So today we're going to talk about differentiability. Now, when we say that a function is differentiable at a particular point, what we're saying is that the following limit exists. And if you remember from before, this is the limit that defines f prime of a. So another way to consider this limit is to just simply consider it as saying that the derivative at a is defined. So that is another way to define what it means to be differentiable. Differentiable means you can take a derivative. What are some of the results of differentiability? Well, first, if we can determine that a function is differentiable at a point, it must be continuous at that point as well. This also means that if a function is discontinuous at a point, it cannot be differentiable at that point. Keep in mind that this is a one-way implication, and that is to say that the reverse implication is not true. So if you start with a continuous function, it will not necessarily be differentiable. So one way to think about this is that if you imagine we've got a Venn diagram and we've got all continuous functions in this big box, the differentiable functions are going to be in this circle that's inside of it. All of the differentiable functions are continuous, but you can have continuous functions that are not differentiable. From a graphical standpoint, we'll say that a function is differentiable if it is locally linear at that point. And to demonstrate that, we'll just look at the graph of a differentiable function. So here is the graph of sine of x, which actually happens to be a differentiable function. We haven't proven this yet, but we're going to use this as an example. Now, if I were to take a specific point over here, which is actually the point pi over 2, 1, and I zoom in on that point, you'll notice that as I zoom in, the function is going to look more and more like a line as I zoom in. And as you can tell, when I zoom in far enough, it's effectively the same as a straight line. That's what it means to be locally linear. That when you look at the graph at a particular point, as you zoom into that point, the graph will turn into a line, or something that's very close to a line. Keep in mind that functions can be differentiable at multiple different points. So if I look at the point where x is equal to 1 and I look at this green point and I zoom in, you'll notice that the function is also differentiable at that point too. Notice that I zoom in and the function turns into a line. That's what it means to be locally linear, and local linearity is the same thing as differentiability. You can find a derivative at a point where it's locally linear. And that should make sense, because that's basically going to be this line that you see here is effectively going to turn into the tangent line if you zoom in far enough. That's one way in which we can define what the tangent line is. So therefore, the function, as you can see here, is differentiable and locally linear. It turns out that there are some notable exceptions to differentiability. Now, most functions that you've seen in a pre-calc class and before are going to be differentiable, but it turns out that if you consider all the possible functions that exist, almost none of them are actually going to be differentiable. But for the sake of this class, the functions that you deal with are going to be differentiable. But there are some exceptions in which you can be able to tell that a function is not differentiable at a point. And the three notable exceptions we are going to consider is if the function has a sharp point at x equals a, then it's not going to be differentiable. We talked about a function being discontinuous. So just to draw this, because I don't have an example to show, if you have like a jump discontinuity or even a hole, it's not going to be differentiable at the point. As you can see, trying to define a tangent line there is going to be difficult. But then the third case, in which on the surface it seems like it follows the rule of local linearity, it turns out that if f of x has a vertical tangent, then it's also not differentiable, because having a vertical tangent implies that, so you have something that looks like this, or probably something that looks like that. Having a vertical tangent at a particular point means that the slope of the tangent line is undefined. So even though I guess you could say it is locally linear at that point, it is not differentiable because the slope of that line is going to be undefined. So now I'm going to show a couple examples of having a sharp point or a vertical tangent. So the most common example that's oftentimes cited as not being differentiable is the function the absolute value of x, and specifically at the point 0, 0. Notice that this function comes to a sharp point at 0, 0. Okay? And if we do try to zoom in on this point, you'll notice that no matter how far I zoom in, this function will not appear to look like a line at that point, at 0, 0, because it comes to a sharp point. If that point was rounded, eventually that rounding out, the curvature would disappear and it would turn into a line, but not in a case like this. So the absolute value of x is not differentiable at 0, 0. Keep in mind that it is differentiable at every other point, because if I zoom into every other point, notice that we do have a line now. So that's specifically for the point 0, 0, for the function the absolute value of x. The next example that I want to look at that's not differentiable is going to be the cube root of x. And notice that if you zoom into 0, 0 here, this is an example where we have a vertical tangent. It is locally linear, but the line that you see here is going to turn into a vertical line, and since vertical lines have undefined slope, it is not differentiable at that point. We can even use the power rule to show that that's not the case. And the last example that I want to look at, which doesn't really fall into the classical categories that we looked at, is this function x times the sine of 1 over x. And really, this is a function that's discontinuous. But notice here, if I try to zoom into 0, 0, you get a really weird-looking function. You don't get anything that looks like a line. I mean, again, at any other point, I can start zooming in, and it will turn into a line, as you can see here as I start zooming in. But at that point, 0, 0, that won't be the case. So local linearity is a good test to see if a function is differentiable or not. That's it for this video. And as always, take care.